The idea that we are living inside a black hole isn't as crazy as it sounds. Black holes warp space and time to the point where space and time reverse roles. For anyone falling into a black hole, the radial dimension towards the singularity becomes time, and the time dimension becomes like space. The two well-known predictions from this are that from inside a black hole event horizon, A, you cannot escape because the way out is back in time, and B, black hole singularity covers a space-like region of space-time that exists like a barrier, so that anything that falls in strikes the barrier simply at different spatial points along the singularity's extent. Another prediction is that the infinitely compressed central singularity of the black hole lies in your future as you fall in. When you reach it, nobody knows what happens because the laws of physics as we know them literally break down. Whatever the theory of quantum gravity ends up being might explain it, but for now we have no idea. The basic idea for the black hole Big Bang theory is that matter from a mother universe collapses into a black hole. The singularity of this black hole is at a single point in space with respect to anyone in the mother universe. But because of the reversal of time and space for anyone inside the daughter universe, that point in space r is 0 become their initial point in time t is 0. Hence, what was a singularity in space is now a singularity in time, just like the Big Bang. This means that any matter falling in from the mother universe will disappear from that universe and emerge at the initial t equals 0 point of the daughter universe, thoroughly scrambled. Not only that, but what emerges at the Big Bang is not just the matter that was there at the black hole's formation, but all matter that ever fell into it. That is because time at the black hole's singularity is essentially perpendicular to time in the mother universe outside. The reason why a whole other universe can be contained inside another one has to do with the strange way in which time and space can be warped, stretched, compressed, and twisted. What appeared to be a dead end at the center of a black hole can instead be a passageway into the birth of a new universe. You can have many interconnected universes this way, in which mothers give birth to daughters which give birth to more daughters, and so on ad infinitum. Thus, far from being only 13.8 billion years ago, the whole interconnected cosmos can be infinitely old, or more properly time-like paths can be infinitely long into the past, passing from universe to universe. The standard Big Bang model of the universe is that the universe, including time, space, and matter, came into being at a single point. From the standpoint of general relativity, the theory of gravity of Einstein, space itself was compressed into that point. As time began, space began to expand, carrying matter with it as it went. This process is still going on, and we know this because when we observe distant galaxies, they are all moving away from us. Moreover, the farther away a galaxy is, the faster away from us it is moving. That is consistent with a theory of the universe, where space is expanding. The more space there is between 2 points, the faster they can be moving apart. The standard example of this is a set of dots on a balloon. Blow up the balloon and all the dots move apart. The dots further apart from each other move apart faster. The center of the universe, where the Big Bang happened, is for us not anywhere in space, but at a point in time, t equals 0 at the Big Bang. So how can we be inside a black hole? One of the odd features of general relativity is its ability to bend space and time to the point where time and space can exchange places. Formally, this is where the signature of the space-time metric changes in general relativity. The metric is what tells us how space and time behave and what distances mean at any given point. Intense concentrations of matter can warp space and time so that the metric changes what space and time mean for different observers. For an observer outside a black hole called the far observer, the singularity is at a point in space. For the observer inside the event horizon, however, the sign of the r and t elements of the space-time metric change places. Now, for the near observer, the singularity is at a point in time, sometime in the future. The horizon problem is a problem with causality. The region over which the CMB is observed to be homogeneous is much larger than is possible for ordinary causality, which is limited by the speed of light. The most popular solution to the problem is called the inflationary theory, in which space expanded exponentially, carrying light and matter along with it so that everything got thoroughly mixed. You can think of it like God's blender. Inflationary theory doesn't solve a number of other problems, including the fluctuation problem, super Planck scale physics problem, initial singularity problem, or the cosmological constant. It doesn't matter exactly what all these mean. The point is that it is far from a panacea. The horizon problem shows that two regions of the universe, as given by two areas of the sky of the CMB, would not have had time to communicate information. In fact, they would have only had about 300 chi to have become correlated since the Big Bang itself. Therefore, they should not be correlated with one another, but only with nearby regions. But we observe that the entire universe is largely correlated. Why the universe has exactly the correct matter density to be flat, called the critical density, is one problem. What that matter is another. We don't know. The universe has three general types of matter: baryons, which are what we think of as matter, dark matter, and a third form. We call it dark energy, and we have no idea what it is. Dark matter, at least, we can observe in the rotations of galaxies and other gravitational behavior. Dark energy we only see in the expansion of the universe. And to explain it, we introduce a constant into Einstein's equations called the cosmological constant, which makes the universe's density even out to the critical density. We believe that if the critical density were not one, then we would not be here. If it were more than one, the universe would have collapsed long ago. Perhaps only an instant after the Big Bang. If it were less than one, the universe would have expanded so rapidly that galaxies would not have formed. It turns out that the only solution that allows a de Sitter space to connect to a black hole is a flat one. Thus, dark energy isn't a form of matter energy, but is actually the result of a spatial topology shape inherited from the black hole. One final point is about the so-called black hole information paradox. Simply stated, this theory suggests that when quantum information in the form of states of quantum particles falls into the black hole, it disappears from the universe. Is it true? Right now it is highly problematic, but it only includes those aspects that we can rigorously demonstrate with experiment and observation. Thank you so much for joining. See you in the next video. Make sure to like and subscribe.